Okay, today is officially about tree diagrams, and we're going to go kind of fast because it's a shortened day. So, possible outcomes. Do you get that there's a 50-50 chance on a normal heads and tails? Let's imagine for a moment that you could weight a coin. It would actually be very difficult, but let's say that you could make it, you're not going to be able to make it 100%. It's going to always be on one side, but unless you cheat and just put heads on both sides, but I'm not talking about that. Okay, but let's say that you could make it 51, then what would that have to be? 49. Do you get that together? These two things will always have to add up to, what do you think? 100, but technically 1.0 because they're decimals, right? It's the same idea. 100% or 1.0. Okay. Now, if I say it's a 5149, and I'm going to stick with that just because I think it makes a better example than just 50% all over the place. Then if I flip the coin again, where am I going to go with that? You start another column here. You don't have to draw a line like that, but after that has happened, then it's either this or it's that, because it depends on what got flipped in the first place, right? So if I was going to do two flips of a coin, then it could either come up heads, tails, or heads, tails again, and let's stick with the whole 51, 49, 51, 49, and then what do you think you do to figure out the probability of heads, heads? Don't overthink this. What do you think I do to find heads, heads? And these two numbers, take a guess. You're going to multiply them. Grab your graphing calculator. You're going to be using, you don't have to use a graphing calculator, but I think that's the only one you probably have. You're going to be doing a lot of multiplying of decimals today. If you need to borrow one of mine, hurry up and make it quick here. Okay, so if you multiplied 0.51 and 0.51, I can roughly do it in my head. It's about 0.25, but I know it's not exactly. What did you get? 0.26. All right. Now, we could do that for this whole chart. Except, do you get two of the multiplications would be exactly the same? I want you to think that through. Do you get that this spot here and this spot here would be exactly the same because it doesn't matter what order you multiply those in. You can still be multiplying 0.51 and 0.49. Go ahead and do that. Multiply that one out and tell me what those two branches come out like. And we'll round to 2 decimal places, which, yes, could mess us up a little bit, but I'm going to let that be okay. I'm going to just move these over a bit so I have room. This is going to be heads, tails, and the top one was 0.26. What's the next one? Point what? 0.25? Does it round to 0.25? All right. And then the next one's 0.25 because they have to be the same, right? And then the last one, which is tails, tails. Notice that's what this is. A tails and then a tails, because tails never fails. What does that one multiply out to? 0.24. What do you notice about those 4 things that we just multiplied out? They add up to 100% again. That makes sense. Because those are the only things that could happen if we flip a coin twice. Do you get that we could make a chart further? If we wanted to make 3 flips, we could, but the chart would start getting really big and really unwieldy. All right, this is the part where I usually tell people, these charts are really good. They work for almost all the probability questions that we will have. But the problem is, by the end of this unit, we'll be doing stuff that even though these could solve it, it would take you literally an hour to make the chart, which you would then use to solve the problem. They just take a long time to make. They're really cool, though, if you only have 1 or 2 events happening. All right, so how would you use this to answer the question? Well, here would be a typical question. What's the probability with this weighted coin of getting either 2 heads or 2 tails? What do? You know what to do? I'm afraid you're doing something else. So let's focus on the question at hand, because people that are watching the videos at home will want us to stay focused here. Okay, so 0.26 was 2 heads, and 0.24 was 2 tails, and I said or. Do you remember when I said that or? Was that going to increase your probabilities of winning? Yes, it does. Because if I win, if you have this, or another kid has that, I just increased my chances when I said or. Okay, so yeah. I add these together and I get 0.26 and 0.24 makes 0.5. There's a 50-50 chance that I'll either get two heads or two tails. You think of them as the rare ones, right? But they could both, when put them together, they make up, that's pretty likely. Is it more likely it's going to be a head and a tail? No, actually, that's the same probability. They're here and here. And I would say this or this, so that means I would add them together. All right, next, here's one that a lot of people do the slow way, but somebody smart's going to figure out the fast way. What's the probability I get at least one heads? That means I get this or that. I think you just figured it out, I think. Either that or you're just using the classic, oh, even though I don't understand it, I just, oh. No, you think you probably do. Well, at least one heads means it's this or that, which, yes, you can just add them all up, and that is, but that's not the fast way. Who can see the fast way? Yes? Tell me. Yes, you. What do you think the fast way is? 1 minus 0.24. I knew what you meant. 1 minus 0.24 would do the same thing, but faster. And why does that matter that much? It's just adding three numbers. Who cares? What if the chart was actually of 8 coin flips in a row? Do you get that there'd only be one bottom number? And it would just take 1 minus that. It would be way, way, way faster. See what I'm saying? Otherwise, 8 coin flips would have like 64 possibilities. You'd have to add up everything except that one case. Do you get what I did there? I took 1 minus having it not happen. All right, so let's do another one that's similar to that. I want to make another example of a chart. So here's a chart, but it's not this one. Let's actually make this chart. So he's got 2 classes. Nope, I'm wrong. He's going to randomly choose one student from each class. So my outcome is either they're going to be a sophomore or they're not going to be a sophomore. It's kind of like flipping a coin. One of the hardest things about making a chart like this is figuring this out, because a lot of people will go, well, he's got 3 classes, so I make a branch for each. Nope, that's not the event. What is the event? He picks a kid in his class. And that kid's either going to be a sophomore or not a sophomore. Everybody please make a branch like that. A branch of your tree. I'm sensing a couple of people may not be with me. Please get with me right now so when I roam out there, you won't have a not completed chart. Okay, next, we put on the branch the probability of each of those things. Now, I may not know the decimal, but it's fine to put fractions for them. If I read the problem further, it says each class has 20 kids, and there's 12 sophomores in his first class. I seem like I meant to underline that, not erase it. There. First class has 12 sophomores, so what do I put as my first choice? How many out of how many is his probability of getting a sophomore? How many sophomores are there? That's what I want. Whenever you get stuck, always go back to what I want over what's possible. Well, how many kids are there possible? No, there's not 60 kids. I mean, picking one class at a time. So I'm in this first hour class, like you're not my first hour, but let's say you were my first hour. And there's, how many kids in here? It says on the problem. 20. How many sophomores are there? It says on the problem. 12. So then there's a 12 in 20 chance that I will get a sophomore. Like in this hour, right this second. How many of you guys are sophomores? Raise your hand if you're a sophomore. It's only like 2. Okay. In my last hour, it's like 18 sophomores and 14 freshmen. All right. Anyway, so then, the not case. You can do this by logic. Think about that. If these two together have to add up to 100%, then there was a what in 20 chance of picking a not sophomore. 8 in 20 chance that I would pick a not sophomore. Keep the chart going, please. If you haven't already got to this part, get to this part. All right, now we're going to make our second choice. Notice it's blue. It's this blue column here. And it's either going to go this way or this way. There's two choices. And in my second choice, which is like second hour, I'll either get a sophomore or not. And I'll get a sophomore or not. But the probabilities change there because now there's still 20 kids. In that first hour, I have 12, and oh, it's pretty much the same on these. Do I just copy those all the way down? Nope. The 12, 8. Actually, I'm sorry. I was kind of leading you the wrong direction. I do just copy those down. Sorry. Something is wrong and I'm confused why. Thank you. Thank you. All right. So it's supposed to be, I'm going to undo. In my second class, this is my second class. I keep thinking I'm in the same class and I'm picking a second person, but that's not what second choice is. This is my second class. Now the numbers are different. There we go. Second class has 8 sophomores, so therefore it's 8 out of 20, and that means not sophomores must be 12. I wish they would use different numbers than 8 and 12 again, because it's really confusing because it's like backwards from the first hour. Okay, anyway, and then again, all of these will be the same because this is his second class, so all of those will be the same. 8 and 20 and 12 and 20. And then last, we have to go to the third choice. Whoa, these get really big and nasty. Do you see why these are not super helpful on a complicated problem? Because you have to make a gigantic chart. But once you're done making the chart, it's actually extremely easy to get the right answers. All right. So in that third class, he has 10 sophomores. So we're going to go sophomore, not 10 out of 20. And that means 10 out of 20. And that's going to be the same the whole way because this whole green column is his third hour. 10 out of 20, 10 out of 20, 10 out of 20, 10 out of 20. And 0.5 and 0.5, because that's the same thing as 10 out of 20, right? I probably could have been doing that the whole time. Now, here would be a typical question we would ask on the test. We wouldn't say that you have to draw the chart, although actually we might on one of the problems. But you could use the chart to answer this question. What's the probability he'll pick a sophomore, and then a sophomore, and then a not sophomore? And we'd say that like this: probability sophomore, comma, not. That means first he gets a sophomore, then he gets a sophomore, then he gets a not a sophomore. Well, there's only one route on this table that gets you there. And I'll show you using my Neato highlighter tool, if I can find it here. Highlighter. And I'm going to use this crazy blue color. I think that might work the best. So that would be, here I start with sophomore, and then I get another sophomore, and then I get not a sophomore. Not a little hard to see that ending shading there, but that's the route that wins, so to speak. Sophomore, sophomore, not. What do you think I do with all the fractions? Well, first of all, don't add, because it could add up to more than 100%. And if anything ever does that, you know you're doing something wrong. If your fractions could possibly add up to more than 100%, you must be doing it wrong. All right. Yes, sir.
So why do you want not sophomore as the third one?
Because that's what the question was. Here's the question on the test. What's the probability of sophomore, sophomore, and then not sophomore? I know, I wasn't doing that question. Okay, I wasn't doing this question yet. Okay, just hold on. Sophomore, sophomore, and not sophomore is my question. So I just highlighted the route. It goes like this. So you would take 12/20ths, also known as 6/10, also known as 0.6 if you wanted to be efficient on your calculator, times 8/20ths, also known as 4/10, so 0.4. And this last one's 0.5, so it's 0.6, 0.4, and 0.5. Get all multiplied together. Use your calculator and do that. Do it slow way if you want to, but multiply those three together. I want to know the answer to my question first. Then I was going to ask you to do the one that's on the board later. Okay. What do you get when you do the 0.6 times the 0.4 times the 0.5? What do you get for that? Yes. 0.2 what? 0.12, okay. 0.12, okay, I just screwed something up there. I'm going to go back to my regular pen here. So there is a 12% chance of that happening. Do you get that once the tree is made, it's not too tough? All right, do you remember me saying that there was this shortcut way that could keep you from having to do a ton of work? That was for this question. First, I'm going to have you do the one that's on the board. I'm sorry, I'm rearranging it. The one that's on the board here. What is the probability he will select 3 sophomores? Go ahead and find that. 3 sophomores. Just use a calculator. Multiply them out. It's not that tough. What's the probability of 3 sophomores? That's going across the top. 0.12 again. So why is that the same? Well, because the first 2 numbers were the same, and these last was an equal chance, right? All right. There's my probability of 3 sophomores. Now my question is, what's the probability instead of 3 sophomores that he'll get at least 1 person who's not a sophomore? Out of his 3 picks, what's the probability he'll get at least 1 person that is a sophomore? Well, there's 2 trains of thought on this. Kids will go, okay, at least 1 means this would work. That wouldn't work. Would the next spot work? Yeah. In fact, you'd have to figure out all of those. And it's this, and or means add. And you would either add up all 7 of those things, or, what's smarter? 1 minus 0.12. Because 1 minus 0.12, which is 0.88, would be what the other ones would have to add up to. It's just logic. All of these have to add up to 100%. I can either add up everything except this top one, or I can take 1 minus the top one. That's a theme. You may not even totally understand it right now. But if you find the thing that's really rare, like, oh, you get all sophomores, that was unlikely, then you take 1 minus that, you'll get the probability of the thing that's more likely. All right, do you get that for this week, it's possible it could rain every single day? Do you think that's likely? If you figured out the probability that it would rain every single day, came out to only like an 8% chance, then do you could reverse that and then go, what's the probability we'll get at least 1 day of rain in there? See what I'm saying? And then you wouldn't say 8%, you'd say 1 minus the 8%. See what I'm saying? There's a fast way and a slow way to do these, so I'm trying to show you the fast way. You could have done it the slow way and added up all of these 7 other answers, or 1 minus that. Okay, that covers pretty much everything that you need to know. Last thought, the replacement thing is a big deal because it tells us independent versus dependent. I'm going to use an example here in my classroom. I have these rocks. Let's say I have a lucky rock in here. Okay, and it's got a red dot on the rock. This isn't it. Well, how would I tell what my probability is? I'd have to tell you how many rocks there are. And there's even some things that would make this not random. Do you get if there's a bigger rock in here, it actually has a higher probability of you grabbing it? Okay, but let's assume for a moment they were all exactly the same size and therefore more equally likely to be grabbed. Okay, so you reach in there, or you were in a dark room where you couldn't see the red dot, right? Okay, and you grab one. What's the probability you're going to get it? 1 out of 1,000. 1,000 rocks. probably not really 1,000 in here, but let's say that there is. Then do you get if I keep that out now, there's a higher chance of getting it? That means that that experiment was what kind? Dependent or independent? Because it depends how many rocks I've taken out. See what I'm saying? That would be dependent. If I use replacement, it's called, and I put the rock back in there, now it's independent because it doesn't matter whether I got one before. Now my probability goes back to 1 in 1,000. That make sense? Okay, the one on the board. Is it dependent or independent? There's one word that tells you. Is it dependent or independent? It's dependent because you're not replacing the marble. So that means it changes your probabilities. So here's the common mistake on this. Kids go, probability of white one. I know this. It's 6 out of 11, 6 out of 11. That's actually right for the first part. And then they say red one. That's easy. Red one is 5 out of 11. And I multiply them. And that's really close to right, but it's not right. What changes on the second one? It's 5 out of 10. You are correct. Can you tell me why? Because you didn't replace the first marble, so there wasn't 11 anymore. Does that make sense to you? All right. So when they don't replace the marble, it makes it more complicated. You got to think about how many marbles are left. What if I added a third one to that, and then this makes it more interesting yet. I have a 3 marble combo, white, red, and then another white. What's the probability of that? Would you please add that third fraction in and tell me if I made it white, red, white, now it's a probability. It's even more complicated because the top part has to change too. This one's white. This one's probability of a red, but there was already one taken out, so... All right, so here's what people think. They just go, oh, so you're saying white, so then it's 6 white ones out of, and then this must go down one again, 6 out of 9. Nope. What's different? What's wrong? What's wrong with what I just said? There's a white one missing. So there isn't 6 white ones anymore because we already got one back here. So now there's 5 out of 9. Do you get what I just did there? Because now there's only 5 white ones left because we got one on the first draw. So now there's only 5 left out of, and there's only 9 left. Why? Because we took 2 out here and here. So now there's not 11, there's down to 9. All right. So then, if I asked you to figure out one more, what's if it was white, red, white, and then another red? Probability of this keeps going down because you keep multiplying these fractions. It's less and less likely you'd get that exact sequence, right? Be really unlikely. What's that last red one going to be then? This spot. 4 out of how many marbles were left? 4 out of 8. I think you got the idea. All right, that's the most complicated thing we could throw at you. So your homework is the evens on tonight's worksheet. You can slavishly obey the evens. Don't try to worry about what do I do with the letters? Do I do even letters? No, we're just going to simply do the even problems. That's it. And that's all I have for you for the lesson for today.